me start the recording. Right. So today topic is earthing or grounding, which is the most important part, right? Which is most important calculations and the drawing. So my screen and voice both are okay, right? We can start now. Uh,
Yes, sir, they are okay.
uh, Akbal, I hope it's okay for you as well. Okay. Yeah. So I have pointed out the agenda that what we are going to discuss in the earthing, which is like wider than the syllabus. We are going extra than the syllabus or than whatever it is in the syllabus. So what we are going to discuss in the earthing or in the grounding. So the difference, like which is more dangerous, the AC and the DC, which voltage is more dangerous for the human, for a person, and whether current is dangerous or the voltage is dangerous for the human, and then what is earthing, why earthing required, and if system is or equipment is not earth, then what is the like drawback, why it is hazardous if system is not earth, and then type of the earthing for the system for the equipment, and then type of the system earthing, difference between grounding and the earthing, like this is like most of the time we use the two name for earthing, few times we say grounding, few times we say earthing. So is there any difference between both name or both are identical? So regarding that we will discuss, and then we will discuss about the NGR. The NGR stand for the neutral grounding resistance. So that NGR, why NGR is required, the NGR selection and then NGR rating calculations, right? That we will discuss, and then if in case we don't have the neutral, we don't have the star point for the grounding, in that how we can convert a ungrounded system or a system who don't have the grounding point in a grounding system, how we can convert that. So about that we will discuss, and then we will discuss about the grounding transformer, which is a bit difference from the normal power transformer that we use. So about the grounding transformers, and the zigzag transformer, like this is a special transformer that we use for the earthing purpose. So how this we do the winding in the zigzag transformer, why this name is zigzag, and about their selection, applications, and their calculations for the rating calculation for this transformer. And then after this we will come on the substation, and for that we will discuss about the substation earthing calculations and then drawing preparation as well, and few checkpoints when we do the earthing calculations or when we uh, uh, prepare the earthing drawing. So this is a like brief content I have prepared during for this earthing session that we are going to discuss. So let us go one by one, let us go step by steps, right? So first let us start with the basic concept, with the basic understanding, as we most of us know that DC is dangerous compared to the AC, because DC is constant, AC is variable, so DC would be more dangerous. But when we refer the standards, when we refer the theoretical books, so they have a little bit different opinion. So we will see that opinion as well, right? So let us start with the basic concept. Let us see that for the human body, which is whether current or the voltage which is hazardous. So let us start with the basic concept. First, let us see whether the current kills or voltage kills the human body. So the answer is current kills the human body, not the voltage. So current is hazardous. Second, whether the AC current or the DC current, which current is dangerous for a human body. So, as per the IEEE standard, which we use for the earthing, So IEEE 80 and IEEE 142, which is we use for the commercial buildings, and IEEE 80 that we use for the power installations. So as per the IEEE 80 clause number 5 in this standard, in this book, in the clause number 5 and the sub clause 5.1, this book is telling, not this is not my opinion, the human body can withstand 5 times more DC current compared to the AC current, which means the AC is more dangerous than the DC current. Right? I'll show you the. I took the extract from the IEEE 80 just for a quick reference. So here, if you see, this is IEEE 80. This is clause number 5, range of tolerable current. How much current a human body can tolerate, and under this clause 5, under the sub clause 5.5, effect of frequency of the current. So in this clause, this book is telling that humans are very vulnerable to the effect of electric current at frequency of 50 Hz or 60 Hz. Current of approximately 0.1 ampere can be lethal. Research indicates that the human body can tolerate a slightly higher 25 Hz current. See, your current depending on the frequency. So slightly higher 25 Hz current and frequency, slightly higher current human body can tolerate when the frequency is lower, and in case of DC frequency is 0, and approximately the 5 times higher DC current. Am I clear with this snapshot, with this extract? I took the extract from the
Yes,
IEEE
sir.
for the quick reference, because IEEE is again 100 or 200 page document, so we cannot go entire 200 page. So just to support my statement, just to support my statement over here, I took the reference from the IEEE at the frequency of 300 to 1000, and again they are telling at frequency of 3000 to 10,000 Hz. In this range, even higher current can be tolerated. This is the scientist name. In some cases, the human body is able to tolerate very high current due to lightning surges. The International Electrotechnical Commission (IEC) provides curves for tolerable body current as a function of frequency. So please, this is important. Current is a function of the frequency and the timing as well. How much current for how much time a human body can tolerate. This is for the quick reference. Yeah, so the current is hazardous compared to the voltage, and when we talk about, when we say current, so AC current is more dangerous compared to the DC current, as per the IEEE, and how much current a human body can withstand or tolerate are the tolerable body current value. So when we are going for the earthing, when we are going for the grounding, we should know how much current a person can tolerate, right? So the standard is telling a 50 kg person, because it will depend on the body weight, or the weight of the person. Based on that, the resistance and the body structure decided. So a 50 kg weight person can tolerate 116 milliampere current. The timing is more important for 1 second. Whereas the 70 kg weight person can tolerate higher current, 157 milliampere current for 1 second. Again, what I'm telling, this is not my value. I'll tell you the reference. So this is the reference. Go to the IEEE 80 again. Go to the clause 6.1 duration formula. Here is the formula. That formula we will also use. But if we check the result, so the result is 116 milliampere for 1 second, 116 milliampere for 1 second. And if you are decreasing the time, means if you ask for zero point 0.1 second, so the same person can tolerate 367 milliampere. This is for the 50 kg person. And if you see over here, this is 6.2 alternative assumptions. So 157 uh, I think milliampere for the 70 kg person, right? So based on the IEEE 80 clause 6.1 and 5.1, I hope this both is this all this three question is clear, right? which AC current and DC current, which is more dangerous, and the tolerable body current. Okay, so that's the first point: human current tolerance and danger between AC and DC voltage. Yeah. Now coming to the next point, what is the earthing? Let me ask from all of you, because earthing is very common and open topic in every electrical installation. We use the earthing, not only for the substation, everywhere. So what is your uh, thought process
Yes,
about
sir.
the earthing? What is the earthing?
It is done for protection of humans as well as from of the electrical equipment from damaged due to the if the current comes.
Okay, let me hear others as well.
To maintain
Srikant,
GPR,
Srikant, okay, GPR, okay, Girish, yeah,
earthing for grounding the fault current,
okay,
discharging the fault current.
okay, discharging the fault current, right? Yeah, Akbal, you wanted to say something?
The protection of human and the machineries.
Yeah, so for both, for the equipment as well as the human protection, right? Human safety, for the equipment as well as the human safety, for both purpose, right? So if I tell you what is the earthing in a very simple, in a very simple, what is the earthing in a very simple language, not going with the technical stuff, in a simple language, what is the earthing? So you all telling why earthing is required, but my question was what is the earthing. So what is the earthing? So as any electrical equipment stands on its foundation, when the equipment is standing on its foundation, so this is already on the earth. Foundation is on the earth, foundation is on the ground. So equipment is already on the earth, is already on the ground. So why additional earthing we are indicating, why additional earthing we are talking? So the electrical equipment stand on its foundation, so it is already on the earth. So why again we are talking about an additional earthing system? So the answer, what is the earthing, or when we say earthing, so in that case what we do, so the additional earthing is the connection of the outer enclosure metal body of equipment above ground. it, I just you can take this photo as a reference: equipment outer enclosure which is placed above ground above ground to a metal electrode pit placed below the ground by a metal strip called the earthing. We can say earthing is metal to metal connection via a metallic strip. This is earthing. What is the earthing? If anyone asking, the material of the metal strip could be or maybe copper, galvanized steel, MS mild steel, or GI galvanized iron, and selection shall be done, means out of copper, steel, which material we are going to take. So that selection shall be done based on the project technical specification or project requirement, the material selection, and what should be the size of that material, what should be the size of that metal strip or metal conductor. So that size shall, that strip size shall be as per the specification if it is mentioned in the specification, or shall be based on the calculation. So we will discuss both the cases. We will see some project in that it is mentioned, and if it is not mentioned, so we will discuss how to calculate the strip size for the earthing purpose. So that calculations we will do, right? In coming slides we will discuss. So this is what is the earthing, and now let us discuss why earthing and difference between earth and unearth system, or why earthing is required. So due to the aging factor, like the behind about the earthing, so due to the aging factor or the weak insulation material of the equipment, during the manufacturing time, or if the material is okay at the manufacturing time, but due to the aging factor, if the insulation material weak inside the equipment, then current can flow from the inner conductive part towards the outer enclosure metal body of the equipment, and thus the fault may occur inside the electrical equipment. Just if in case, if we take a wider aspect for the electrical equipment, we can say that any electrical equipment is made by the three major component. The first the first component is the inside conductive, which is metal conductor, and after that we have the insulation layer, and after that we have the outer enclosure, and that could be a metal also, right? Can we divide any electrical equipment like this in a wider aspect? In a wider
Yes,
aspect.
sir. You told us about the solid insulator and the hollow insulator. So there you.
Yeah, yes. So the first inner side, which could be a metal, and that is the conductive part through that the current flows, and then we have the insulation part, which isolate the inner metal from the outer metal, and then we have the outer enclosure metal, which is for the mechanical protection to the equipment. Outer enclosure, right?
Armor, yes.
Outer
You
enclosure.
kept.
Outer enclosure. Right. So this is the three component in any electrical equipment in a wider aspect. In a wider aspect, as a common aspect. So if in case your insulation due to the aging factor is weak, or the material is not the correct material at the time of the manufacturing, if insulation failures, in that case there is a possibility to flow of the current from the inner conductor, inner metal, towards the outer metal. And since this incident occurring inside the equipment, which cannot be seen outside from the equipment, which cannot be seen outside, and a person could be exposed to fault current or short circuit current if they come into touch with the damaged or faulty equipment outside enclosure body. If the person comes with that in touch with the faulty equipment outside enclosure body, so that could be exposed to the short circuit current. Now consider the case if the equipment is unearthed, then the total fault or short circuit current will appear on the outer enclosure metal, and due to that the electrical potential outside of the equipment have been increased, and if the person gets in touch with the equipment outer enclosure body, then the fault current may start flowing via the person to the ground. Therefore, to avoid these situations, we must provide earthing to all the electrical equipment. So here we are talking about the human safety purpose, as well as we do the earthing, and that earthing we call it the grounding. We do the grounding of the equipment for the equipment protection purpose as well. That we will discuss in below slides. Right? I hope this point is clear, that why earthing, and if system is unearthed, so what could be the case? Yeah, that is the case of the motor, Amir, correct? Now, and this is not applicable only for the live charged operational equipment. This concept would be applicable for the spare equipment as well. What I mean by this, the spare equipment, let us case a transformer. Let us consider a transformer. So and not only the live operational equipment, but the spare equipment kept in store as a backup, right? Which may have a static charge, which may have the static charge, also needs to be connected to the earth system. For example, we need to provide the earthing for the spare transformers, because if you see in the spare transformer, we have the oil in the main tank, and the radiator is connected with the main tank, right? So uh, so what will happen, the continuously the oil the oil keeps circulating through the radiator tank, through the radiator. Am I correct? Are you connecting with my point, what I'm trying to
Sir,
say?
yes, sir. Due to flow of oil in the
Yes,
transformer
sir.
will develop the static charge that can be hazardous.
Yeah, so the current keeps circulating, and why the current keeps why this oil keeps circulating? Because we know that
Cooling, yes, sir.
there is a difference in the temperature. The oil which is when the oil suppose this is exposed to the sun, so there would be like solar heat that will come on the transformer oil transformer tank, and that will come more on the upper side of the oil, right? And so in that case the density of oil will reduce, and the oil which is on the bottom side, their oil density will be higher. So due to change of this density in this oil liquid, they keep circulating, the oil keeps circulating inside in the tank and the radiator in between that, right? So due to that circulation of the oil, there is a chance to develop the static charge on the outer surface of tank as well as radiator surface. So to eliminate this static charge, we need to provide the radiator and main tank body earthing to discharge the develop static charge in the ground. So the earthing is not only for the live equipment, this is applicable for the spare equipment as well. Am I clear so far? Am I clear so far? Like
Yes, sir.
the AC and DC current, then tolerable current, what is the earthing and why earthing required, and why earthing required for the spare transformer and the DG oil tank, why that need to be provided the earthing. Now let us consider the case. This is for the equipment earthing. Let us consider the case for the system earthing, means for the neutral earthing and neutral grounding. If that neutral of a transformer is not grounded, in that case what could be the hazardous? To explain that situations, let me go through with via ETAP. I take one example. Suppose just to save the time, I am going with a developed SLD, right? I think we have already discussed how to draw these SLD in the ETAP, so just quickly going through with the concept. So here we have a grid. Here we have a grid, right? And the grid is 33 kV. And then this grid we are feeding to a transformer which is 33 by 11 kV transformer, and which is 10 ampere transformer. And here we have the 11 kV voltage on the LV side of the transformer, and that 11 kV voltage we are feeding to a 11 kV panel board, right? And that further connected with the different loads, right? And here we have the breaker and CT relays, all these things, right? And let us take the transformer and go to the transformer edit box and go to the grounding tab, and here we can select the grounding of the transformer. So we are taking the primary, delta, secondary, star, and let us go with the solid grounding, effective grounding, which generally we use, right? And if any line to ground fault case occurred in that system, then what would be the current and what would be the voltage? Let us see. So if I simulate the short circuit in this system, so I'm taking 60909 standard, right? And if I run the short circuit, so here that we can see the 6.94 kilo ampere the fault current, and the fault I'm taking on the 11 kV bus. Here the fault happened. So if the fault happened here, the 6.94 kilo ampere current is injected from the source to this 11 kV bus, right? 11 kV bus, and
Yes, sir.
at the same time 6.44 kV is the voltage, and that is okay, because here we have the star winding, right? So in the star winding we can convert for the star winding, the phase voltage would be line voltage divided by root 3, right? I just wanted to see this 6.44 kV, how it is coming. System my 11 kV system. So in when we have the star winding, so in that case, the voltage that will appear on the phase, that would be phase voltage, and 11 kV is my line voltage. So 11 kV divided by 1.732, it will give us the phase voltage, which is 6.35 something. So it means 6.44 kV in the round figure. It is coming over here. So far it is okay. This is a normal system. Suppose you are your earthing of the neutral is isolated. Let us take that after some time your transformer neutral earthing is opened, right? You are not taking any earthing, or accidentally it opened. In that case, what would be the case, or what would be the hazardous on the system? So I'm taking the same secondary star and the grounding, but I'm going with the open grounding system, right? Click OK. So here we can see delta star, but this star is not grounded. In that case, if at that moment if any line to ground fault occurred, so could you see what the change in the system parameters, in the system parameter, what the change occurred? You first of all your current becomes 0, right? Ah, am I,
Yes, sir.
am I
Fault current becomes zero when as we open the star side of the transformer.
Yeah, let me take the snapshot. Let me take the snapshot. Grounding, I'm going with the first solid grounding, and then just stick with the concept which is more important, right? So I'm taking this case. First of all, when your neutral is star and this star point are the neutral busing of your transformer connected with the ground, and then this is the output of the system, right? And now after some period of the time your neutral is grounding is opened, right? There is no earthing. In that case, if by the chance if the ground to fault line to ground fault occurred, so what is in your system, what the system change, right? You can see the effect of the grounding. Your fault current becomes 0 kiloampere, which was initially 6.94 kiloampere. This is one change that happened, right? So means that this CT and the relay could not sense the fault current. Even the fault current is happening, fault current is flowing, but that could not be detected by the relays and the CT, because there is no return path. There is no return path to flow the current back to the source, and
Yes,
here
sir.
we can put the CT and the neutral, and that neutral current transformer can sense that current. But since no path, so no current sense. This is the first.
If NCT can sense, then the protection system will also act then.
Yeah, will also activate if your NCT there and current flowing through the neutral, right? When the current flowing through the neutral, then neutral CT will sense those current, and then it will give input to the earth fault relays, and those earth fault relay will give the tripping command to the associated circuit breaker, right? And your voltage again, six, it changed from 6.4 kV to 11 kV. It jumped the voltage, right? Means on your phase initially it was flowing, it was coming 6.4 kV stress, but in this case on your each phase 11 kV stress is coming. So what would be the, then what would be the case, that whatever the cable we are taking here, that cable, if in case we have considered the earth grade cable, so in the earth grade cable we take the voltage insulation, insulation voltage based on the phase voltage, but on the, in that case on each phase the voltage will come as the line voltage instead of the phase voltage, right? So your cable insulation may also damage.
Yes, sir.
Ah, let me take the opinion with others as well, Aswin. We are going on the right. I think are are you getting the point? What we are like discussing over here?
Yes, sir.
Yeah, right. So this is a okay, Santosh, if it is clear to you and Piyush, yeah, it's clear, then we can understand. Okay, so if it is okay, right. So this is the drawback if your neutral is ungrounded. So same exercise we have listed over here. In addition, if the neutral point of a star connected transformer is ungrounded, then the line to ground fault current could not be sensed. Could not be sensed because, yeah, because it is not flowing, that could not be sensed. This is the one reason that could not be sensed. Uh, and then, okay, we'll discuss. Let me complete now, guys. Let me complete. Could not be sensed. Then could not be sensed, and time, at the same time, at the time of the line to ground fault, and the phase voltage will increase to the line voltage level. So this is disadvantage in the system if system is unearthed. If system is unearthed, right? Coming back to the type of the earthing system, how many earthing system we have? So for any electrical equipment, usually we take two type of the earthing system for the electrical equipment. So as you can see over here, this is a neutral bushing of the transformer which is connected to the ground with help of the metal strip, right? To isolate with the metal body, here we have provided the insulators. This is another one picture. Another picture, if you can see over here, here the neutral is connected as well as the outer enclosure body of equipment is also connected to grounding grid or grounding mat. So considering these two cases, are we can say there are two type of the earthing system we do for the electrical equipment. First is the equipment earthing and second is the system earthing. Equipment earthing used for the human body protection. Equipment earthing for a human body safety for human body protection, and the outer metal body of equipment is connected to the ground. This is the for the equipment earthing. At the same time, the system earthing, this is used for the equipment self protection, not for the human protection. Equipment self protection. And in this system, earthing is made by connecting the neutral point or neutral bushing of the generator or the transformer to the ground. Here, the case that here we have the neutral point or neutral bushing, and that we are connecting to the ground with help of a earthing strip. So broadly, two type of the earthing we do for the equipment earthing or the system earthing. And the purpose equipment earthing for the human protection, system earthing is for the equipment protection, equipment earthing for the human being protection, system earthing for the equipment self protection. Let us take one by one case. So let us discuss first system earthing, which is equipment self protection, right? So system earthing, as discussed, system earthing is used for the equipment protection and the neutral bushing is connected to the ground. Additionally, this connection could be made directly to the ground or through a medium or via a medium. Here, if you see in this case, so here we took this neutral bushing and connecting with help of metal strip directly to the ground. There is no any medium in this picture we have used. So this is a direct connection, or we can do connection through a medium or through a additional equipment. In the sense of medium, through some additional equipment. So if direct connection to the ground, then it is called solid earthing or effective earthing, right? In this case we have the solid earthing. We are connecting this neutral directly to the directly. So this is the case for the uh, solid earthing, right? If you see here, this is the case for the solid earthing. Okay, let me take this grounding, and instead of open, let me put this solid. So I'm taking solid earthing. So here if you see this neutral point or the star point, which is connected directly to the ground. So this case is called as the solid earthing, right? uh, Chris, please mute yourself, and please you message
So
me.
this is required only where the equipment have its own neutral point.
Yes, yes.
System earthing is applied for the where the equipment has earthing, neutral point.
Yeah. And but there is a problem with associated with the solid earthing or solid grounding. If line to ground fault occurred, an approximate 85% fault type is the line to ground fault. A huge amount of current may flow towards the transformer bushing or towards the transformer, which could damage the transformer. This is the problem with the solid earthing. Therefore, to avoid damage of the transformer or to limit the huge line to ground fault current, resistance could be introduced between the transformer and the earth, between the transformer neutral bushing and the earth, and the neutral grounding resistance method introduced in the electrical system. This uh, point we can see over here as well. So I'm taking the same transformer going to the grounding, and here taking grounding with help of the resistance here, and then if you see here, this is resistance. So here this is not direct earthing, this is earthing via a resistance, right? And this system called as the this resistance called as the neutral grounding resistance. And why this neutral grounding resistance is introduced over here? Just basic concept to
Limit the
to
LG fault current.
for the equipment protection, and this equipment protection we are achieving by limiting the line to ground fault current, right? But there is a drawback. Of this NGR system as well. Means this NGR system is also not the foolproof system. There is a drawback. But there is a drawback of the NGR system also. When we limit the fault current at any phase, the other remaining two phase voltage gets increased from phase voltage to a line voltage. Let us see this statement with help of the ETAP as well. So let me go first via solid grounding, and then let us see uh, what is the voltage on each phase. So let us see the fault type, and let us see phase voltage ABC indicating RYB. So let us see in each voltage what is the phase voltage. So here we can see here that that 6.41 kiloampere. I am taking line to ground fault current. So in only one line fault happened, right? So in that 6.41 kiloampere flowing, in the remaining two line there is less, only 200 current is flowing, right? At the same time, if we see impact on the voltage, so on the faulty phase we have 0 kilo voltage, but on the Y and B phase, suppose R phase is faulty, so on the remaining two phase the voltage remain same as phase voltage, 6.4 and 6.4 kV, and the Y and B voltage. But what the problem? If I go with the if I wanted to limit the 6.41 kiloampere current, if I wanted to reduce this current, and to reduce this current I'm inserting the resistance over here, and suppose I wanted to limit the current from 6.4 kiloampere to 100 ampere only, just 100 ampere current we wanted, we want allowed to flow. In that case, let us see the impact on the voltage. So when I introduce the resistance, which is which only allowed to flow 100 ampere, we'll discuss about the resistance calculations, right? So if you see I'm limiting 100 ampere, it means this is limited 0.97 kiloampere, means 100 ampere roundabout, right? But could you see the impact on the voltage? Initially it was 6.4 kiloampere. Now the voltage jumped to 11 kV approximately.
Yes, sir.
So drawback of the
Yes,
NGR system also, when we limit the fault current at any phase, the other remaining two phase voltage get increased from phase voltage to line voltage. This is what in statement number one. Due to this reason, the NGR method is not used for extra high voltage. In EHV, we not use NGR. Never. Never means generally not use. I cannot say never, but generally not used. NGR method is not used for the extra high voltage, and used mostly for the medium voltage and high voltage, because in the medium voltage and high voltage level is less. say 11 kV, 33 kV, 3.3 kV, and 6.6 kV only, right? So in that case, my voltage is less. So if it is jumping from phase voltage to line voltage, then that could be manageable. But if you have 220 kV or 400 kV and that voltage is increased, in that case, your if voltage increase, then your insulation cost will also you have to increase. So your entire system cost increased too much. As the higher voltage needs a higher insulation requirement, so overall system cost will increase. Therefore, for the extra high voltage substations, we go for solid earthing, solid grounding, as the equipment is already designed for higher short circuit rating due to the grid requirement. Plus, we don't have any rotating equipment. For that, we need to limit the current. Equipment can handle the fault current. No need to reduce the level of the fault current. And NGR is used for the medium voltage and high voltage electrical installation, where the rotating machine is used because a huge line to ground fault current may damage the core of the rotating machine, right? So to protect the core of the rotating machine, see, if you take any rotating machine, we have the core, and on that core we do the winding, right?
Yes, sir.
So if your winding is damaged, so you can unwind and you can rewind at the side. You can rewind. Rewinding is easy and that could be done. But in case your core is damaged, so that core cannot be fixed at the site. You have to send back this machine, that motor, that generator back to the factory, right? So in that case, your plant is completely shut down. Plant is completely shut down. So that risk cannot be taken. Cannot be taken. So we always uh, use the system for the core protection of any rotating machine. And if fault current is flowing through the equipment who have the core and winding, so core winding as well as your core could damage or could saturate. In case we have rotating machine, in case we don't have rotating machine, in that case there would be no stator, no core if static equipment. But in case of rotating equipment, we have the rotor, stator, core. This concept is applicable in the equipment, right? So then in order to limit the so we have to limit the fault current in those kind of the electrical installation. So in order to limit the fault current, and that limitations we do in the range of 400 to 600 ampere approximately. And to protect rotating machine means I am reducing the fault current. I am reducing the fault current to protect the electrical machine core. So to protect rotating machine like generator core, motor core, these kind of the rotating machine, NGR system is used, right? So that it can
Yes, sir.
limit the fault current, and it can protect the rotating equipment. But in case of the
When
substation,
you are teaching the this module 3 transformer, then you also mentioned this same thing. Yes.
yeah. I'm waiting for 1 minute. You adopt this statement, then I will go forward. You take your 1 minute to fully understand this topic. I took a I took a electrical substation for just for the reference. And here if we see, so we have the surge arrestor, CVT, CT, disconnector, breakers, conductor, right, towers, and here we have the transformers, right. We don't have the motors. We have here in the substation. If it is a generating substation, generating power plant, in that case, to the generation side, not to the substation or switchyard side, to the generation side, if we are using the thermal power plant, right, the conventional power plant, in that case, there would be the motor and generator. For in that system, we have to use the NGR, right? Okay, so let us discuss a comparison and a conclusion between two groundings, between two earthing systems. So if we do the earthing by the solid earthing, so advantage in the solid earthing, advantage, the current flow too much, the extensive or huge current flow, extensive flow of line to ground fault current enables accurate detection of ground fault, because so much current flowing, so we can easily detect the fault current. So this is the advantage for the solid grounding, but there is so many disadvantages. Disadvantage means it allows the third harmonic and multiple of third harmonic current to flow in the system. Second, ground fault current magnitude is high. The core damage at the point of the fault in rotating machine like generator and the motor will be high. So the disadvantage for the solid grounding. In the substations, all equipment is static equipment, so solid grounding would be suitable and no any problem at all with the solid grounding. Right? Resistance grounding system advantage. Resistance grounding limits the fault current to a low value to avoid core damage in a rotating machine winding. Winding damage is tolerable, but core damage is not tolerable. So resistance grounding limit the fault current to a low value to avoid core damage. Resistance grounding reduce the burning and melting in electrical equipment. Resistance reduce mechanical stress compared to the solid grounding system. It reduce re-strike or arcing fault because your current have been reduced. So obviously re-strike and arcing fault would be reduced compared to the ungrounded system and compared to the solid grounded system as well. But there is a disadvantage by NGR. When we limit the fault current at any phase, the other remaining two phase voltage gets increased. So this is a drawback of the NGR system. Now coming, let us discuss difference between grounding and the earthing. Uh, two words we most of the time we use. So first of all, there is no any difference between grounding and earthing. Both are identical, right? But if we wanted to differentiate the name wise, just the name wise, that where we will use the grounding name and where we will use the earthing name. So just the name wise difference, technically no difference, both are identical, but conventionally or in practice where we say grounding and where we say the earthing. So grounding represents the connection of a current carrying parts such as neutral can also carry the current at the time of the when the system is unbalanced. So current flow in the neutral when the system is not balanced to the ground. Grounding represents the connection of current carrying part to the ground. It is mostly either generator or transformer neutral. Hence, it is popularly called neutral grounding. Because we connect neutral to the earth, but we say neutral grounding. We not say neutral earthing. Most of the times we say neutral grounding, right? Because when we connect a current carrying part to the ground, so we call it the grounding or the neutral grounding name. And grounding is for the equipment safety. In the case of a resistance grounded, system, the resistance grounding system limits the core damage or prevent the core damage in the stator of a rotating machine. In the case of solidly grounded system, large ground fault current flow enable sensitive fault detection and fast clearance of the fault. This already we have discussed in the previous slide as well. Whereas earthing represents the connection of non-current carrying parts to the ground, like the metallic outer enclosure of equipment, the outer enclosure of the equipment which not carry the current or which is not designed to carry the current, right? So the connection of non-current carrying parts to the ground called as the earthing, right? So outer enclosure of equipment and the earthing done for the human safety mainly. Let us see one example. Under balance operating condition of power system, the earthing system does not play any role. When your system is balanced, earthing don't have any role. But under ground fault condition, it enables the ground fault current to return back to the source via neutral without endangering human safety. Let us see here. We have the generator and the transformer, right? So here we have the generator R by B phase, and here we have the neutral point. So if we connect this neutral to the ground, so we call neutral grounding, right? Similar case with the transformer, the LV voltage and the HV voltage, and suppose we have both sides the star winding. So if we connect this neutral or star point to the ground, so we call as the NG, neutral ground, neutral ground. Parallelly, if we have the outer enclosure of the generator or the outer enclosure of the transformer, if in case we connect the outer enclosure metal body to the ground, in that case we call this is earthing, right? Am I clear with the difference between the earthing and the grounding? Earthing and the grounding? Yeah. Okay. So
Yes.
yeah. Okay. So if it is clear, let us go and let us see. Let us see how the return current flows and the type of the resistance grounding. So here we can see a case that here we have the alternator. So here we have the field armature and the star winding over here, RYB phase and neutral, and that neutral connected to the ground. It is called neutral grounding. So we say neutral grounding and equipment earthing, right? So here if the fault occurred, line to earth fault, line to ground fault occurred. So the fault current flowing to the ground, and then it is flowing through the mass to the earth, right? And at the same time, via flowing through the ground, it reached to the neutral point, a neutral grounding, where it get a return path. Here we have the NGR as well, and it flows back to the system, to the source. Current have a nature that it flow towards the low resistance path, and it tend to flow towards the source as well, right? So here we can place the CT and that current we can sense. So this is a case that how current flowing back towards the system. Further, this resistance which we are using for the neutral grounding, divided in two types. The low resistance grounding, where the short circuit current is limited in the range of 100 to 800 ampere. Low resistance grounding. Second, it could be the high resistance grounding, where the short circuit current is limited in the range of 10 to 15 ampere. But which resistance grounding we have to follow, or how much current we have to limit? How much current we have to limit? And the exact fault current value needs to be selected, or how much fault current we wanted to limit, so that to be selected based on the rotating machine core withstand capacity value, that how much current core can withstand without damage, without going to uh, damage, how much current it can withstand, and which is provided by the equipment original manufacturer. So we need to check with the manufacturer what is the core withstand capacity. So if we conclude the discussion so far, what we discussed about the grounding and earthing, if we conclude the discussion, so conclusion is that the main purpose of a neutral grounding resistance is to limit ground fault current to safe values, so that all the electrical equipment, rotating electrical equipment in a power system is protected. Rotating equipment, not all the electrical equipment, so that all the rotating electrical equipment in a power system is protected, right? So let us see about the resistance calculations in the neutral grounding resistance. What should be the value of resistance, right? The fault current should be kept in the mind while deciding the NGR value. Too high value of NGR could limit current to a very low value, which will not able to activate earth fault protection relay accurately. In general, we allow current in the range of 100 to 800 ampere in this range to flow through the neutral of the transformer, and that we will sense. So let us consider that the maximum fault current flow through the resistance allowed is 100 ampere. Therefore, the current carrying capacity of the resistance is 100 ampere. And let's suppose the system is 11 kilo voltage system, that we can see over here as well. We can see over here as well that system is 11 kV on the secondary side, LV side 11 kV, and this 11 kV is the star connected, right? Star connected. So on each phase, how much voltage will come? 11 divided by root 3. 11 divided by root 3. So that would be 6.351 V in phase voltage, right? So we know the voltage, we know the current, how much current we are going to allow, and we are going to allow 100 ampere current. So we can apply here simply the Ohm law, right? We can apply the Ohm law and we can calculate the resistance ohmic value. Simple, V is equals to IR. So R we can calculate. That would be V divided by, and this is kV, right? This is kV. 6.351 kV convert into the voltage V, divide by how much? V is equals to IR. R would be V by I is 100 ampere. If in case, so R would be 63.5. Right? So therefore the current capacity of resistance is 100 ampere, and let's suppose system voltage is 11 kV. Then the phase to ground voltage would be 11 divided by root 3, and just apply the Ohm law to get the resistance value of NGR. So V is equals to IF into R. IF is my fault current, which I'm going to allow 100 ampere only. So R would be V divided by IF. R 11 by root 3, which is 6.35 divided by 100. Resistance value is coming 63.5 ohm resistance we have to apply there if we wanted to reduce, if we wanted to allow only 100 ampere of the current, right? So we can see this in a clear photo. Star winding neutral connected to the ground, called NGR, neutral grounding, not the neutral earthing, right? And fault happened, ground fault happened, and current flowing through the neutral to the back the transformer, right? If we wanted, we are going to allow only 100 ampere current to flow in the system, right? So resistance current going allowed flow 100 ampere. So we know the voltage phase between the phase and the ground, we know the voltage, right? And we know the current, so the resistance value could be easily calculated, right? Just apply the Ohm law. This concept, when we convert into the Excel, so how we calculate the NGR through the Excel sheet. So I just took one case study, just for the NGR. Let us see. Here we have the transfer rating 7500 kVA. In this case, we have taken the 10 MVA transformer. 10 MVA transformer. Suppose this is a 7.5 MVA transformer, right, which convert into the kVA. Voltage primary 11 kV, secondary 6.9 kV or 6.6 kV. Impedance 8. Rated current at 6.6 voltage side of the transformer 627.55 ampere. So ISC here, ISC ampere means rated current at 6.6, voltage AC this much, and short circuit current 6 to 75.55 ampere. I have to see this how why it is mentioned over here. Fault kV 75 ampere. System charging current typically 1 ampere per 1 MVA for medium voltage system considered. So the let through current of the NGR should be at least 10 times higher than the system charging current. So the NGR required minimum let through current 75 into 7.5 into 10. But this 75 ampere value we can ask to the rotating equipment manufacturer as well, that how much current core can withstand and how much current we need to limit over here, right? So this means this is not important to calculate each every time this value. And from the above, it is evident that minimum rating of NGR should be 75 ampere, considering the stability during the system charging. However, the NGR selected for limiting the fault current to 5% of the symmetrical fault current, which works out to be 314 ampere. So 5% of the system fault current rating, here we have the 6275, which to be 5%. So NGR selected an NGR rating selected for 10 seconds as a protective device will clear the ground fault in less than 1 second, depending on type and magnitude of the earth fault. So NGR current rating 315 ampere. Here two value, minimum should be 75%, maximum allowed, in our case we took 100 ampere is allowed, but in this case there would be any technical specification in that it is mentioned that 5% of the fault current is allowed, and the fault current is 6 to 75. 6 to 7. So this fault current already we have calculated through the ETAP as well, how much fault current is coming. In our case 6.4 kiloampere is coming, but in this case if it is 6 to 75, 6 to 75 into 0.05, so 313 means 314 or 315 ampere, that we can see over here. 5.02% they are going to limit, and this percentage might, I took one reference of the NGR sizing, and that 5% will be based on the technical specification of the project, and if not mentioned, in that case we have to check with the equipment core withstand capacity, how much current that can handle without damage. So that current would be our NGR current rating, right? And NGR voltage rating, so voltage rating 6.6 kV divided by root 3, that would be NGR voltage rating, which is 3983 voltage only. Value of resistance, so just VYI, and the same thing also we have done VYI, we know the V 3.983, V divided by I, which is 315, so 12.65 ohm would be the NGR value. Same concept based on that we have seen in here, the same concept that we have seen over here, right? And in that calculation there is another step, that if cable has been used to connect the NGR with the transformer, so what should be the cable size, minimum cable size to connect the resistance to the neutral bushing. So as the NGR rating is 10 second, that usually we take. I will come on that why 10 second we take. The cable need to be sized for a maximum 10 second. So I think IS equals to A divided by uh, uh, I A is equals to ISH under root T divided by K. This formula also we have seen during the cable sizing calculation. We have decided the cable size in the cable module, right? So same concept apply over here. Same concept apply over here. Current is 315 kiloampere, which going to flow, right? K factor 143 because we are taking the XLPE copper cable. So 143 for aluminium 94, that value of K we take, and fault clearing time or fault withstand time that we are going to take as 10 second, right? So putting the value A is equals to ISH under root T. So ISH means 315 kiloampere into T means under root 10 divided by K means divided by 143. In that case, we can calculate the minimum size of the cable 6.97, but that cable we are not going to use because we have our voltage is 6.6 kV. So we have seen what is the minimum cable manufactured on the 6.6 kV. That minimum cable we have to consider. If you see, as per the calculation, requirement is 7 square mm only, but we are going to take 370 square mm because 70 square mm is the minimum size which is available on the 6.6 kilovoltage level. Due to that purpose, I took this example just if in case you see this kind of the calculation for the NGR, so you can also tackle or can also understand this calculation due to that purpose. Yeah, we have learned this formula already, right? Now we are talking enough about the NGR. Let us see how the NGR looks like. How the NGR looks like. So could you see here? This here we have the resistance. Could you see here? So we have an enclosure panel. In that enclosure, we put the resistance. And there is a if your line to ground fault current is too much high and you wanted to limit that fault current in 100 or 200 ampere, then your resistance would be bulky. At that application, NGR is not suitable. We will discuss that application as well, right? It is not suitable. So now when the amount of fault current to be restricted is very high, then the size of the NGR becomes bulky, plus it is not economical in the cost, right? Plus it dissipate too much too much heat, right? When the large line to ground fault current flowing through the resistance, it dissipate the heat as well. In that case, we choose another type of the earthing system, which is NGT. NGT stand for the neutral grounding transformer, and few times we may use the combination of the NGR, and that NGR rating is small rating NGR plus NGT. NGT stand for the neutral grounding transformer. Means we are going to connect a transformer on the neutral of a big rating transformer, right? A small transformer we are going to connect. So whenever plus another application, whenever we have a power transformer which is delta connected, we don't have the star, we don't have the neutral point. If no star, then no neutral. If we have delta winding, right? So whenever the delta connected transformer winding at the LV side, in that case also we have to use the NGT system, neutral grounding transformer system, to create the artificial grounding in the electrical installation. We will see this concept through some drawing as well, right? So here, if you see here, delta is star. Here we have the star, so here we have the neutral. But if in case this is delta connected and that delta connected towards the LV side, towards the secondary side of the transformer, towards the distribution side of the transformer, right? If we have the delta. So both solid grounding and resistance grounding are impossible when we have LV winding that are delta connected, since there is not any neutral or star point available in the winding. Then the grounding of these three-phase delta connected LV winding is achieved via the grounding transformer, as the grounding transformer create an artificial grounding neutral connection on an ungrounded three-phase system, are a three-phase system who don't have the grounding point, grounding bushing. In those kind of the system, it create the artificial grounding. We will see that with help of the drawing as well. And further, as we discuss about the resistance, that there is two type of the resistance: high resistance and low resistance grounding. Similarly, in case of the uh, transformer, neutral grounding transformer, we use two kind of the transformer for the grounding purpose. The grounding transformer could be two types. One, this grounding transformer could be star delta connected, just two winding star delta connected transformer, right? Another, it could be the earthing trans or the grounding transformer could be a interconnected star, or this interconnected star called as zigzag single winding transformer. Two options available in case of the NGT, and there are two purposes achieved with help of this grounding transformer application. It create artificial grounding. Second, it limit the single line to ground fault current, same as NGR do, right? And out of these two, zigzag, because zigzag is a interconnected star and single winding. So due to that purpose, zigzag is smaller in size. Zigzag transformer are smaller in size than any two winding star delta transformer. Right? Let us see this both transformer through the drawing. So here if you see, as I told, if we have a power transformer and the LV side or the distribution side we have a delta, which is the case over here. This is 132 by 33 kV, and 33 kV side we have the delta connected winding. We don't have the neutral, but we have to do the earthing for the secondary side. Why we have to do the earthing? Because if we don't do the earthing, so we could not sense the line to ground fault current. So due to that, we have to do the earthing, we have to do the grounding. So how this grounding can be done? For that, what we just take the tapping from the conductor, and we can connect here this resistor and the disconnector. This equipment just for the protection of this transformer, earthing grounding transformer. And here we take two winding earthing or grounding transformer, right? And here we can, on this side, here, could you follow my cursor? Here we can put the CT, here we can put the CT, and if any ground fault occurred, ground fault current will flow back to the source with help of this neutral connection of the star delta, right? By this, and here we can sense that current. Plus, so this is the case of the two winding transformer. Second, star delta connected two winding. Second, if you see over here, this is a auto transformer star. This is 400 by 220 kV and by 33 kV. So 400 step down to 220 kV, it is going to the 220 kV system. And now further we have tertiary 33 kV voltage winding, right? We have discussed that why we take the tertiary winding, what is the advantage, how it works as a stabilizing windings, right? So and that winding connected into the delta, and this going to feed to the LVEC system of the entire electrical installation. As you can see, 33 kV switchgear it is going to feed. So to achieve the grounding on this part of the circuit, we are going to use this zigzag transformer, and this is single winding as I told. So only one circle you have to achieve, right? And this is interconnected star, so that's why this we take this type of the zigzag line, not the straight line, to represent this zigzag transformer. And further, as I told, we put the CT, and that called the neutral CT, and here neutral bushing CT, and it connected to the ground. And when the current will flow through this, here we will place the earth fault relays, and through that we can detect the earth fault current, and we can provide input to the protective relays to disconnect or isolate the system. So zigzag here two winding transformer, and this is the case of the uh, neutral grounding transformer. Let us discuss about the star delta. Is I think it is clear to all of you. It is not a new name. Zigzag is a kind of the new name. So let us discuss about what is zigzag and how this zigzag transformer is made. So as I told, this is a single winding. So here if you see, we have a three limbs single, and on these three limbs we are doing double winding, double winding, right? So R phase, Y phase, B phase means this RYB we are going to connect over here. R phase, Y phase, B phase we are going to connect over here. So R phase we are taking, Y phase we are taking, B phase we are taking, and that we are feeding to this here RYB phase, right? If you see over here, let me take the snapshot just for a clear understanding. Interconnected. So R phase coming over here, if you see, it is going this, then going on the back side of the core, then coming on the front side, going back side, coming front side, going back, and then it is coming out, then interconnected. So it is now going to connect with the another limb. It is going over here, again connected, going back, coming front, going back, coming front, and then finally the last point going to connect with the neutral, right? Means last point, here we are making one last point connected to the ground. Similarly, so similarly y y it is going over here, going over here, going over here, this coming down, coming, interconnected star. Could you see? Interconnected star B, and similarly here we have the Y. Three limbs, each limb is provided with the two identical winding, right? These windings are wound such that, means now you can ask me one query over here, that if it is connected always with the system, so always we are connected with the ground with help of this transformer, right? Always grounded with help of this transformer. So it means always line to ground fault case, because this zigzag can connect this phase to the ground through their winding, but it is not connected ideally, because two winding will two winding will cross out the flux that we can see over here. These windings are wound such that under normal conditions, when system is balanced, normal condition, two fluxes on each limb oppose each other in such a manner that the net flux on each limb is negligible or small or cancel out. and under the normal conditions it only draw little bit, very little current, just only core magnetizing current, or just current only to magnetize, right? Just to magnetize. Let us see another example. So here we have the star delta winding. On the right hand side, if you see, R phase going to here, Y phase, and then B phase, and then this all going to connect with the ground, right? So this is the system or winding for the zigzag transformer. And during a phase to ground fault, when the phase to ground fault occurred, the zigzag transformer's coils magnetic flux is no longer equal in the faulted phase. During a phase to ground fault, the zigzag transformer's coil flux is no longer equal in the faulty phase, not in each three phase, in the faulty phase only, which allows, or faulty phase allows, a line to ground fault current to flow, right? Hence the purpose of a zigzag transformer is to provide a return path for the earth fault current and the delta connected system. At the neutral side we use the CT, which can sense the return earth fault current and provide output to the protective relay to give a tripping command to the associated circuit breakers. And for the sizing of zigzag transformer, a short time rating, as we have taken for NGR 10-second rating, similarly we take the zigzag also. Short time rating is applied, ensuring that impedance is not too low for the desired fault limiting. Our resistance should not be too low for the desired fault limiting. We have the transformer, that is why the resistance word we are indicating by the impedance word, right? Here we can see one another example. Here we have the ABC means R by B phase. Here we are connecting this zigzag transformer. Suppose here line to ground fault occurred. Now this fault flowing here, neutral point here we have. So now here the current will get three paths to flow: I by 3, I by 3, I by 3, right? I by 3. So this I by 3 over here, I by 3 over here, and then this I by 3 over here, right? We will discuss zigzag transfer sizing calculation in the detail. This is a case that the if fault current is flowing, then that fault current will divide identical in three parts. This is what this picture is indicating, right? So if we discuss about the sizing calculations introduction, so should we continue the calculations today for the zigzag transformer, because it is going to take a long time, because a lot of steps we have to do uh, for the next session, next day. Okay, I can feel that there is a lot of technical stuff. Yeah, we will keep the separate session for the grounding transformer sizing calculations. Okay, okay. So I will so in the next session, in the next class, we will discuss about the NGR, sorry, NGT sizing calculations, right? Okay, let me unmute now. I think you can unmute. So let me know if anyone have any query. so far what we discussed about the earthing. So what we discussed, we started from the basic concept, whether the voltage and current, which one is dangerous, whether AC and DC current, and how much current a human body can tolerate. And for this, I took the reference from the standards. And then we discussed what is the earthing, and we discuss here why earthing required, and we discuss that not only the live equipment, even if we have the equipment in which that static charge could be developed, so those equipment also require the earthing. And we
Sir, I
discuss
have a question.
and we
How we
discuss
decide the material type of earthing system and grounding
Santosh,
system?
hold on. And we discuss here about the earthing for the neutral point. If the neutral is not grounded, so what would be the drawback? So this we took the reference from the ETAP as well to understand about this concept, and then discuss about the uh, type of the earthing, and then we uh, took the system earthing first. So first we'll discuss about the system earthing, and then we'll come back on the equipment earthing. So in the system earthing, we have discussed different way for the system earthing. Means we are going with the solid, we are going with the resistance earthing, and we discuss the comparison between both earthing, and we discuss about the word difference between earthing and the grounding, right? And then we took the case for we discussed about the NGR sizing calculations, and then we discussed that if in case the fault current is too much high and too much current you have to reduce, in that case the NGR would be bulky and not economical, so we do not go with the NGR. We take with the alternative earthing, and that alternative earthing is the NGT, or few times NGT with a small NGR, right? So we then we discuss about the NGT, and we discuss that NGT provide a artificial grounding, and we discuss this NGT could be two type. It could be two winding star delta, or it could be a single winding zigzag trafo. And then we discuss then we here we seen few references from the project drawing about the NGT, and then we discuss about the zigzag transformer construction, means their winding, how we do the winding in the zigzag transformer, right? And from the next class onwards, we'll discuss about the NGT sizing calculations. This is what we discussed so far. Now, out of this topic, tell me if anyone have any query. Yeah, Santosh.
I have
Now,
one question.
yeah, thank you.
Yeah, near the cable ceiling ends, sometimes there are some earthing frigates, and we use a portable earth switch,
Mm-hmm.
which is a flexible lead. So that terminology is earth switch or grounding switch, basically.
Yo, that you can say that is the portable earthing switch, because
Okay,
we are earthing. See, as I told that earthing and grounding both are identical. There's no any difference there. So
hmm.
out of two, anyone you can use. You can say portable earth rod, or you can say portable ground rod. Both is accurate.
Okay,
I tell you the difference,
okay,
that if we connect the neutral to the ground, so we call neutral grounding, and if we connect the outer enclosure metallic part of the equipment, so we refer
earth switch.
earthing equipment. Earthing.
Earth.
Yeah, but both
That's
is
fine. So,
identical. There is no any difference.
okay, thank you.
Sir, my question was, you talked about neutral grounding. So neutral grounding will provide where we have a neutral like transformer and generator.
Yes.
What type of material we supposed to be utilized? Like a transformer, we use neutral grounding, or copper. Sometimes you use GI, sometimes you use MS flat. So is the uh, method to
We'll
know
discuss
what
later
type
on.
of
We'll
material?
discuss later on about that.
That
Uh,
will be okay. Will tell.
we'll discuss.
Okay. Okay. Thank you.
So, in recent design, I got a drawing with final distribution transform with neutral grounding. So it's not possible, no?
Sorry, come again.
Recently, I got a design drawing, and it's in UP actually. Uh, where the final transformer has a neutral NGR. So I told it is not possible, and it is not possible. No, I mean, during the fault, the neutral voltage go up. Is it possible?
So that trafo have the neutral bushing.
Yeah, it has a neutral. I mean, actually, I got a design doing only. It's a dry type transformer.
Mm-hmm.
They have a neutral started the connection. Second is a star connected one.
Mm-hmm.
So there they have mentioned NGR connected to the neutral.
Mm-hmm. Okay, you share
Is it
me the case. You share me the case, Sumita. Let me once go through again, and after that I will comment anything.
okay, sir? I'll forward it to you
Okay, okay,
or should they possible?
okay. Yeah, Akbal, do you have any query? Okay, so if in case no query, so we can wind up session for today, right? Okay, thank you, Girish and Sindhos. Girish, I hope that your queries has been resolved. Okay, yeah, thank you, Piyush. I'm going a little bit extra compared to the syllabus, just to have a wider understanding about the thing. Due to that reason, these all things we have not mentioned in the syllabus, but I think this you should know, so that your understanding would be a little bit wider due to that reason. And it is going to take the time as well. I understand, but just it would be beneficial.